DSPy's modular architecture enables algorithmic optimization of language model prompts through composable module components, where each module encapsulates a specific text transformation task defined by natural language signatures. This artifact demonstrates the final stage of the DSPy MLflow integration pipeline, focusing on model loading and inference execution using MLflow's PythonModel interface. We will examine how a previously logged DSPy program is deserialized from MLflow's model registry and invoked for prediction, showcasing the seamless transition from development to deployment while maintaining environment consistency through MLflow's artifact management system.
Import MLflow. Hash load the model as an MLflow Python mod. Model equals MLflow. PyFunc, load model info, model URI. Hash predict with the object. Response equals model. Predict what kind of bear is best. Print response.
This code demonstrates the standard MLflow pattern for loading a logged DSPy model and performing inference. The MLflow PyFunc load model function loads the model from its URI, returning an MLflow PythonModel wrapper that provides a consistent prediction interface. This abstraction allows DSPy models to integrate seamlessly with MLflow's deployment ecosystem, regardless of the underlying framework specifics. The prediction workflow follows MLflow's standard PythonModel contract, where model predict accepts input data and returns the model's response. This pattern enables model interchangeability and consistent deployment across different serving environments. The example shows a simple text input being processed, with the model returning a structured response containing both reasoning and answer fields, typical of DSPy's Chain of Thought modules. This approach provides several advantages. It decouples model implementation from deployment concerns, enables consistent monitoring through MLflow's tracking capabilities, and supports streaming responses when certain conditions are met. The trade-off is the additional abstraction layer, which may add minimal overhead, but provides significant flexibility in model management and deployment scenarios. Let's break it down line by line.
Import MLflow.
Imports the MLflow library for machine learning experiment tracking and model management.
Hash load the model as an MLflow Python mod. Model equals MLflow. PyFunc, load model info, model URI.
Loads a machine learning model from the specified URI using MLflow's Python function interface, storing the loaded model in the variable model. The model info, model URI, parameter provides the location or identifier of the model to be loaded.
Hash predict with the object. Response equals model. Predict what kind of bear is best.
Calls the predict method on the model object with the string input, what kind of bear is best, and assigns the returned response to the variable response. This line demonstrates a direct inference call where the model processes the given prompt and generates an output, which is then stored for potential further use.
Print response.
Prints the value of the response variable to the standard output. The integration of DSPy with MLflow's PythonModel interface creates a clean separation between model development and deployment. By loading the DSPy program through MLflow, PyFunc, load model, we maintain the modular architecture's benefits while gaining MLflow's deployment consistency. The predict method serves as a universal interface, abstracting away DSPy's internal chain of thought processing while preserving its structured output format. This pattern enables seamless model interchangeability across environments, with the trade-off of a minimal abstraction layer that unlocks significant deployment flexibility. The example demonstrates how a simple text input flows through this standardized pipeline, from model loading to inference execution, while MLflow handles the underlying artifact management and environment consistency.
The adapter wraps the question in silence, and the LM spits out answers like a vending machine of wisdom.